Hello friends, welcome to video lecture on fluid mechanics. In the today's session, we learn about fluid pressure at a point, Pascal's law, hydrostatic law under fluid statics point. So let us start fluid pressure at a point. For that, consider a small area dA in a large mass of fluid. Okay? If the fluid is stationary, then the force exerted by the surrounding fluid on the area dA will always perpendicular to the surface dA. Let dF is the force acting on the area dA in the normal direction. We have considered this one small area, okay, dA. Then the ratio of F by dA is known as intensity of pressure or simply pressure, and this ratio is represented by P. Hence mathematically pressure at the point in a fluid at rest. Okay, so we have considered here the small element from this fluid, that's why the dP is written here. Okay, so dP is nothing but dF divided by dA. If the force F is uniformly distributed, if this force F means we consider the total force from this one is uniformly distributed over the entire area or total area, okay, then the pressure at the point is given by this relation. For the smaller element we are considered as dF pressure, and for that smaller area we are considered as dA. And if we consider the total force as well as a total area, then the intensity of the pressure, okay, or total pressure P is nothing but F divided by A. Here F is nothing but the force, A indicate the area. Therefore the force or pressure force F is nothing but A will come towards this side, multiply by A. The units of the pressures are first one kgf per meter square and kgf per centimeter square in MKS units. Okay. Second one Newton per meter square or Newton per meter square. We can write this in this way also. And Newton per mm square in SI units. Newton per meter square is known as Pascal and is represented by PA. Other commonly used units of the pressure are kilopascal in this way equals to 1000 Newton per meter square, and bar equals to 1000 kilo Pascal, okay, equals to 10 raised to 5 Newton per meter square. So let us discuss about the Pascal's law. For that, it states that the pressure or intensity of pressure at a point is a static fluid is equal in all directions. This is proved as the fluid element is of very small dimensions. So fluid element is of very small dimensions, that is dx, dy and ds. Now this will actually appear to here. Okay, this indicate the instead of this delta x, just consider as dx. Okay, so here the dx with us, dx, dy, and for this inclined portion we are considered as ds. Okay, so these are nothing but the dimensions. Let us consider a arbitrary fluid element of the wedge shape in a fluid mass at a rest, okay, as shown in figure. Let the width of the element perpendicular to the plane of the paper is unity or 1, and here unity and px, okay, written here. Okay, so next one py and this one pz are the pressures or intensity of the pressure acting on the face on AB, then AC and BC respectively. Let angle ABC equals to theta. Then the forces acting on the elements are, so first one is nothing but the pressure normal to the surfaces. Whatever the pressure normal to surface. The next one, weight of the element in vertical direction. Okay, the forces on the faces are force on the face AB. So face AB is here, and similarly the force on the face AC. Okay, then next one, the force on the face on BC, that indicate here. Okay, and as well as the weight of the element, means the force acting on this face, this face, this face, okay, this face, and entire weight of this element. Let's just see one by one. So first one is nothing but the pressure force normal to every surface, and next one, weight of the element in the vertical direction. Okay, so just see here, the forces on the faces are, first one, the force on this AB face is nothing but the intensity of the pressure in x direction, that is Px multiplied by its cross section area. So cross section of this face AB. So what's about the cross section of this one face AB? Is nothing but the here to here Px multiplied by, so area of the face AB. So this indicate the y-axis, the x-axis, and this indicate the z-axis. So here in this case, area of the face AB is nothing but the product of dy multiplied by 1. Why we are considered this one as 1? Because the width of this element we are considered as unity or 1. Okay, so we can get the force on the this face AB is nothing but the Px multiplied by dy multiplied by 1. Similarly, the force on this face AB is nothing but here the intensity of the pressure with us y. Okay, and what's about this one? This is nothing but the dx of the delta x, just considered as dx. Okay, so dx multiplied by 1 is nothing but the cross section area of this face AC. Okay, so you can get this one in this way, y multiplied by dx multiplied by 1. So force on the face BC, let us consider this is BC. Okay, so what's about the intensity of the pressure along this direction? Pz. Okay, Pz multiplied by, so what's about this one? Ps multiplied by 1 is nothing but the cross section area of this face BC. Okay, so ds multiplied by 1. Okay, in this way you can get the intensity of the pressure along every face. Then what's about the weight of the element? So weight of the element is nothing but the mass of the element multiplied by here g. So weight, this mass of the element is nothing but the volume multiplied by this one rho. Okay, so we know the definition for the rho. Rho is nothing but the mass density. Okay, so what's about that? Mass per unit volume. Okay, from that we can get this one, volume multiplied by density. So what's about this one? Multiply by g term will remains as it is. So volume is nothing but, this case, this is the triangular shape. Okay, triangular shape with us. So what's about this one? AB multiplied by 1 AC, as this indicate the triangular shape. So 1/2 their height multiplied by this side, and the width of this one with us 1. So AB multiplied by AC by 2 multiplied by 1 written here. Okay, so what's about this one? Rho and g will remain as it is. So in the next part, look to us here, where this rho indicate the density. Rho indicate the density of the fluid. Let us see the next one. Now, if you focus on the forces along the x direction as well as the forces along the y direction, okay, to get the information about the force along the x direction. Now, what's about this one? This force is running towards x direction. Now, this force is in inclined direction. You need to resolve this force. You have to resolve this force z ds into 1. Okay, you have to resolve this force into its component. Okay, so one component will come along this direction. This means here in x direction. so that now resolving the forces in x direction, we have now focus on this diagram once again. Okay, so this one small element we have considered, this force is in inclined direction. Okay, so if you look towards this angle, so theta angle with us, automatically this force is in perpendicular direction to this face. Means what's about this angle? This angle must be 90 minus theta. Okay, so what's about the component of this force in horizontal direction? So the actual value for magnitude for this one, pz multiplied by ds multiplied by 1. Okay, like this one. So the component adjacent with the theta angle is nothing but the cos component, and remaining automatically sine component. So pz multiplied by ds multiplied by 1 into sine of 90 minus theta. Okay, this horizontal component is nothing but this one. And what's about the vertical component? You can get pz multiplied by ds multiplied by 1 into cos of 90 minus theta in this way. Now focus on this one. So whatever the forces resolved in the horizontal direction, okay, for the equilibrium we are just equating that forces with the 0. Okay, now in this case just focus one by one force. Px multiplied by dy multiplied by 1. Okay, this force with us. So this force running towards the right direction, so consider this force as positive. Okay, and apart from this one, this actually running in opposite direction of this force. So pz into ds multiplied by 1 multiplied by 90 minus theta. Okay, so already the minus sign is given for the same, and for the equilibrium just equate with the 0. Okay, so what do we get here? Px multiplied by dy multiplied by 1, this term will remain as it is. And so what's about this one? This indicate the intensity of the pressure along the z direction. By mistake actually here z is not shown, so let us consider this one as pz multiplied by ds. Okay, so what's about this one? Multiply by one term will automatically come as it is. You have to multiply by this term with the inside terms. Okay, so sine of 90 minus theta is nothing but the cos theta. Okay, so from this relation, what's about this one? From this figure, ds multiplied by cos of theta, ds multiplied by cos of theta. So if you just consider this small triangle, okay, so ds is nothing but the length for this side. Okay, so cos of theta is nothing but the adjacent side to the, what's about this one, hypotenuse. What do we get here? Dy by ds. Okay, here what do we get? ds cos of theta is nothing but the dy. Okay, it must be equals to dy is nothing but here length for the AB. That's why AB equals to dy is written. Okay, now from this what do we get? Px multiplied by dy multiplied by 1 minus this one pz multiplied by, so this term ds into cos of theta is nothing but the dy. Okay, now if we take this term towards the right side, okay, this dy get cancelled. So what do we get here? Px equals to pz. Okay, similarly let us consider the forces in vertical direction. Okay, this force vertical in upward direction, this force in downward direction. Okay, so let us consider this force py multiplied by delta dx multiplied by 1. Okay, this force vertical in upward direction and this one in the downward direction. So pz into ds into 1 into cos of 90 minus theta. Okay, so for this force a positive sign is given, as this force running vertically in upward direction, this force we are considered as negative. Okay, for the equilibrium we are saying that equals to 0. Now in this case, if you look towards the vertical direction, along with this two component, one more force with us, so entire weight of this element, so already that weight calculated by us here, AB multiplied by AC divided by 2 multiplied by this one 1 multiplied by rho multiplied by g. So whatever the values of this AB and AC with us, we can just substitute that values. What's about the AB with us? AB is nothing but, what's about the length of this AB? We are considered for the small element as dy, and for this AC, AC is here. For this AC we are considered as dx as the small element with us. If you look to us this one, instead of writing this AB and AC, we have written here for this AB as dy and for this AC as dx. Okay, now look to us here, dx multiplied by dy divided by 2 multiplied by 1 multiplied by rho into g. Okay, so this term as it is taken there, and for the equilibrium we are just equating this term with the 0. Now after that just try to simplify. Okay, so by multiply by dx, this term will come as it is, then dz multiplied by cos of 90 minus theta is nothing but the sine theta. Okay, now the next term minus dx by dy by 2 multiplied by rho into g, okay, equals to 0. But in this case, if you look towards this one, ds into sine of theta, ds into sine of theta from this triangle, ds into sine of theta. Once again focus on this one, ds into sine of theta. Okay, so what's about sine of theta? Front side divided by hypotenuse. Okay, so what do we get here? Can get that in terms of we can just get this value as it is, ds into sine of theta. Okay, this term will as it is. Okay, so in this case ds into sine of theta is nothing but the dx, ds into sine of theta, ds into sine of theta, yeah, front side. Okay, with us you can write for that sine theta equals to front side divided by this one hypotenuse. Okay, so in this way we can get the value for that ds into sine of theta is nothing but the dx, and also the element is very small, hence weight is negligible. Small element we have considered, that's why just neglect this weight parameter. Okay, so we can just simply write here py into dx minus pz into dx for this one, and this product, this one is very small, so weight component is very small. Okay, so we can neglect this. Okay, so we can write in this way, py into dx minus pz into, instead of this ds into sine theta, we'll just simply write here dx is equal with the 0. So in this way you can get py equals to pz. Okay, so from equation number this one 2.1 and equation number 2.2, what do we say here? Px equals to pz and py equals to pz. Okay, so meaning for this one, px equals to py equals to pz. So the above equation shows that the pressure at any point in x, y and z directions is equal, since the choice of the fluid element was completely arbitrary. Okay, which means the pressure at any point is the same in all directions. So now discuss about the pressure variation in a fluid at rest. A pressure at any point in a fluid at rest is obtained by hydrostatic law, which states that the rate of increase of pressure in a vertically downward direction must be equal to the specific weight of the fluid at that point. This is proved as, for that let us consider a small fluid element. Let this one delta A equals to cross section area of the element, delta Z indicate the height of the fluid element, P indicate the pressure on the face AB, the P indicate the pressure on the face AB, Z indicate the distance of the fluid element from the free surface. Here is the free surface. Okay, the forces acting on the fluid element are, just see one by one. So first one, pressure on this face AB is nothing but here P multiplied by delta A, and acting perpendicular to face AB in downward direction. Next one, pressure on CD. So here is the CD face with us. Okay, pressure on this CD is nothing but P plus del P by del Z into delta z, okay, multiply by the area of this small area, cross section area of this side is nothing but the delta A, acting perpendicular to the face CD, vertically upward direction. Apart from this one, the weight of this fluid element, weight of the fluid element is nothing but density multiplied by gravitational acceleration G multiplied by volume, like this one, okay. So the density with us in terms of rho multiplied by G multiplied by volume. So volume here is nothing but, we know the length for this one, height of this one element with us delta Z, and the cross section area of this one with us delta A. You can get the volume in this way, delta A multiplied by delta Z. Now we look towards pressure forces on, pressure forces on the surfaces, this one BC and AD are equal and the opposite direction. For equilibrium of the fluid, you can just write here whatever the pressure force here, intensity of the pressure here and here, okay, that becomes an equal one, okay. Now for the equilibrium of the fluid, you can write like this one. So whatever this force available with us, we can just consider this force into delta A. That force acts vertically in the downward direction. Apart from this one, this force acts vertically in upward direction. So this force will comes as it is, written as it is, okay. So apart from this one, what's about this one? This is nothing but the weight of the fluid element, weight of this fluid element, okay. So weight also acts in downward direction. Here we have considered the sign convention. Whatever the forces acts in downward direction, considered here as positive, okay, and whatever the forces running vertically in upward direction, we have considered that forces as negative, okay. So for the equilibrium, we are just equating the summation of all the forces equals to 0. Now just simplify this one into delta A, just multiply by this term to inside term, minus P into delta A minus, what's about the next term, del P by del Z, multiply by this delta Z multiply by delta A, plus this term will remain as it is, rho into G multiplied by delta A multiplied by delta Z, equate with the 0. If you look towards this term and this term, both the terms are same, okay, get cancelled. Now next one, keep this term as it is and take this term towards the other side. So both the minus sign, actually minus sign from both sides becomes a plus sign, okay. So here del P by del Z equals to this term delta Z into delta A equals to rho G multiplied by delta A into delta Z, okay. Term will remain as it is. Already del P by del Z term, this actually already we have cancelled, okay. Now if you look towards this one, delta Z multiplied by delta A and delta A multiplied by delta Z, both the terms are same. We can just take that term common from this both the term and that get cancelled. So what we get here, del P by del Z, this get cancelled, equals to rho multiplied by G equals to W. So what's about this one? We know the weight density of the fluid. Weight density of the fluid is nothing but the mass density multiplied by gravitational acceleration. Now from this equation 2.4, this equation states that the rate of of pressure in vertical direction is equal to the weight density of the fluid at that point. This is hydrostatic law. By integrating above equation 2.4 for the fluids, we get, now take the integration, just take this del Z towards the right side, okay. So integration of this one del P equals to integration of rho multiplied by G. This term actually come towards the right side. Okay, so instead of writing this one del P and del Z, we can just write this one as D and dz, okay, here. So after integration of this one, what we get here, we have considered this one del P del Z for the small element. We just add all that small elements here. We have taken as integration for all the pressure at the various points. Okay, so what we get here, integration of dp means here you can get the P equals to integration of this dz is nothing but z. So where P is nothing but the pressure above atmospheric pressure and z is nothing but the height of the point from the free surface. So from this equation 2.5 we can get the pressure head, that is z. Okay, z equals to P divided by rho into G. So this rho into G goes in denominator. Okay, so here Z is nothing but the pressure head. Once again, just here Z is nothing but the height of the point from the free surface. Get the height this element from the free surface. Okay. I hope that concept discussed in today's lecture clear to you. Thank you.